Okay, thank you all for attending this second Applied PD seminar of the spring quarter at the University of Washington. Of course, this is this seminar has been an online seminar long before that became a fashionable thing. We are very happy today to have Massimiliano Berti from SISSA in Italy talking to us today. He is, I believe it is 10 p.m. his time. No, sorry, 8 p.m. his time?
8 p.m., yeah.
We have this online format. I'm sure it's not the first online talk for people, but you are welcome to interrupt the speaker if you want, or keep your questions to the end. You're also welcome to put them in the chat, in which case we can read them to the speaker if that is your preference. Without further ado, I'll hand over to Massimiliano, who's going to give us part two of the talk that was given by Alberto Maspero last week. Massimiliano will talk about the full description of the Benjamin-Feir instability of Stokes in finite and infinite depth. Go ahead. Thank you.
So, first of all, I wish to thank very much Bernard for organizing these seminars and all the support of Anastasia for today. So this talk will be in fact the second part of the talk given by Alberto last week concerning the Benjamin-Feir instability spectrum of the Stokes waves in finite and infinite depth. I will first remind the results presented last week, and then my goal will be to today describes the main ideas and the techniques of proof, which looks very natural for this problem. So I'm going to describe, in fact, Stokes waves, that is traveling periodic waves, so a rigid periodic profile which travels at a certain speed, c, the speed c, which depends on the amplitude u, on the amplitude of the periodic wave u. And so these waves, I'm going to consider waves for bidimensional fluids, that is for fluids which in one direction looks constant. And then we shall consider ocean on a bottom, which may be either finite or infinite. So I will first remind the well-known equations that were presented last week, but I prefer to remind them. So we are discussing the water waves equations, which are the Euler equation for a fluid, which fills a time-dependent region, delimited from the bottom is minus h, and then a time-dependent periodic free boundary. Then the equations of motions are given by the Bernoulli condition of continuity of the pressure at the free surface, the other kinematic condition, which tells that the particle on the fluid remain on the surface forever. Then we are considering here velocity fields which are irrotational, then which are expressed as the gradient of phi, a velocity potential. The fluid is incompressible, the velocity of u is equal to 0, so the velocity potential is an harmonic function in the domain occupied by the fluid. And then this other one, it is the impermeability condition, which tells the derivative of phi respect to y is the y component of the velocity field, so it vanishes at the bottom. The unknowns of the problem are the time-dependent domain and the velocity potential. So this is the picture, well known. So here it is the time-dependent region occupied by the fluid u, and then we have an equation in order to determine phi, the harmonic function phi, and the free boundary. So it's important, several algebraic structure of the water waves equation has an extremely important impact and have extremely important consequences. One of them, it is the fact that it is an Hamiltonian system. It is an infinite dimensional Hamiltonian system, which, as observed by Zakharov, can be written in the usual classical Darboux form, that is defining the two the vector of variables e of x and psi of x, the previous set of equations can be recasted as a Hamiltonian system in Darboux form, that is J, which is the Poisson tensor, assumes the usual form 0 identities minus identity 0. The canonical variable psi associated to eta turns out to be the trace at the free boundary of the velocity potential. Then the system looks, in fact, can be recasted as an equation for these two quantities defined only at the free surface, and they are an Hamiltonian system. Here appears this object, which is the Dirichlet-Neumann operator, which is the operator which, taken the Dirichlet datum at the free surface, solves the Laplace equation with this Dirichlet datum, and then produces the normal derivative of the velocity potential. Another symmetry which has extremely important consequences for the dynamics of water waves, it is reversibility. Also, reversibility stems from the Newton equations coming from Euler, and it is written explicitly in this fact that the Hamiltonian of the water waves equation is left invariant under the action of this involution rho. The involution rho is the one which takes eta psi and then changes x in minus x and changes the sign of the momentum component. And the fact that it is Hamiltonian, the fact that it is reversible, has extremely important consequences for the dynamics of the water waves. For example, there were essential ingredients in order to prove the existence of quasi-periodic solutions. They are an essential ingredients in order to show that the solution of the water waves equation are well posed for long times for all the normal form constructions, and they actually have an extremely important consequences also for the stability of the water waves. And then today I would like, in fact, to stress this point and explain why they really are important to be exploited. They give a lot of symmetries which otherwise are hidden. Okay, so Stokes waves, I repeat. So our solutions e of psi of the water waves equation, here written in the Zakharov formulation, which are a rigid profile, eta hat psi hat, which travels with a certain speed c. Then the particular shape of this form shows that, of course, in a moving frame which travels with speed c, they are stationary. So these are the water waves equation that now I can write them in a reference frame. So when we apply Galilean transformation, it turns out that the water waves equation just look these systems of equation, where the fact that we are in a moving frame with speed c produces these two red terms here. And then, as we said, in the reference frame moving with speed c, the Stokes waves are equilibrium, so are the easiest possible solutions that we can expect. And then we look for equilibrium solutions. So eta of x and psi of x, where the right-hand side vanishes. And then Stokes produced approximate solutions. The rigorous convergence proof was given by Levi, Civita, and Nekrasov in infinite depth and infinite depth. And then it turns out that there exist solutions, eta epsilon psi of x, and a certain speed c of epsilon, which have a certain expansion. They are analytic in the parameter epsilon, in the amplitude. And then here I've reported the fact that okay, according in any finite depth, there are special coefficients. And of course, in order to have explicit computations, they have to be carried out. C of epsilon is a hyperbolic tangent of h, and it is the speed of the linear frequency of the linear Stokes waves. So the Stokes waves starts from this ch, which is a linear independent of epsilon. So this is the speed of the linearized theory of the linear Stokes waves, and then there are some nonlinear corrections here. Okay, then as it was presented last week, I remind, but it's important, Stokes waves appear in families parameterized by 4 parameters, which are amplitude, epsilon, like here. For any epsilon, we have a 1 parameter families. And then the invariance of the equations under space translation. In fact, here the bottom is flat, so all the equations are invariant under translations. Then there is the fact that the velocity potential is defined up to a constant. So in fact, here the constant psi0 is can be adjusted. It is the fact that also the pressure of the fluid corresponds to the fact that the pressure of the fluid can be defined up to a constant. And then there is another invariance so that, for example, in infinite depth, writes as follows, that translating eta of a constant amounts just to add here to solve the problem, in fact, with another pressure. So here I wanted to emphasize, recall the fact that Stokes waves appear in four-dimensional manifolds, and then this will have consequences on the linearization. So as discussed last week, we wanted to discuss the linear stability of the Stokes waves. So we linearize the Stokes waves, the water waves equation at the Stokes waves. And then after a couple of transformations, which are called the linearly good unknown, a form of that had been introduced by David Lann almost 20 years ago in order to prove the first rigorous results about local existence of the water waves, and then another straightening Levi-Civita transformation. It turns out that we have to study, we obtain a system, a linear system. We have to understand that this a linear system where L epsilon is an operator which has this explicit Hamiltonian form. So it is the Poisson tensor given before, J, and then there is here a self-adjoint symmetric operator. And the fact that L epsilon, in addition, it inherits the property of being a reversible operator, which explicitly means this invariance. And here, this function A epsilon and P of epsilon are explicit functions, which depends on the linearization of the Stokes waves. Then they are all analytic in epsilon, they have an explicit expression, and they are 2π periodic and even. Okay, and then the questions about the stability of the Stokes waves is to know, okay, the spectrum of this operator L epsilon, the spectrum of this operator L epsilon. Then, say, for example, the block of Floquet theorem tells that the spectrum of the operator L epsilon on L2R, it is in fact the union of the spectrum of the operator L nu epsilon, which are this Floquet operator, which acts on 2π periodic functions. And in particularly, then, if for some mu we obtain an eigenvector V with certain eigenvalue lambda, then there exist solutions which are block wave solutions of the system discussed before of HT is equal to HT equal to L epsilon H of this form here. In particular, then, if here we see that lambda is, for example, so if lambda has a positive real part, the solution H grows exponentially. Okay, so then the recipe in order to construct the block Floquet operator given a pseudo differential operator is that one substituted the variable psi with psi plus mu, and then the outcome is that, as it was explained the last time, we have to study the spectrum of a pseudo differential complex pseudo differential operator of this form. So J is still the same. Now here B of epsilon is a complex operator. Here we see that there is I mu, and which is self-adjoint. This operator, we see that it contains one derivatives because of here, and also here because the Dirichlet-Neumann operator is a pseudo differential operator of order 1. So L mu epsilon, in fact, can be regarded as a bounded operator from H1 into L2, with mu epsilon self-adjoint and which commutes with this complex involution rho bar. And then recall rapidly the theorem presented by Alberto last time that now I will present its proof. So one defines, we call the Berti and Benjamin function, which is this certain function, which grows explicitly in H. It vanishes just at a certain specific depth, which is almost H1, the famous one, H137, and so on. And then the theorem roughly tells that if the depth H is larger than this threshold, then there exist two unstable eigenvalues that are completely described and which form shape 8. And then in shallow water, on the other hand, in shallow water, there are all the eigenvalues still remain purely imaginary. Okay, then let me give the more precise result. The more precise result starts defining, we call this the Benjamin-Feir discriminant function, which depends on the amplitude epsilon and the Floquet exponent mu. It is this complicated term with these coefficients, which are completely explicit. In particular, e2 is this positive function. And I stress this because it is important to know the sign of this discriminant function. And so in particularly, we see that, so for H below H, the critical depth of Witt and Benjamin, so this is negative, this is negative because e2 is positive, and so the discriminant will be negative. And then this will imply that the eigenvalues will turn out to be only purely imaginary, whereas if H is greater than this depth, then we have here a coefficient which is positive, whereas so it means that if mu is small enough, well, so this term is negligible. So, and if mu is small enough, also this term is negligible, so the discriminant function will be positive for mu small enough. And that is here the notation that I will always use, so it's better that I explain. So when I write something like this, we mean a function of two variables, which it is analytic in epsilon and mu, so which can be written as an explicit power series, can be expanded in epsilon and mu, and which starts with the zero, the lower order terms are these ones. Okay, then the theorem discussed by Alberto with obtained together with Alberto and Paolo Ventura is the following. Okay, so here I write so if H is larger than the critical depth, there exist eigenvalues, lambda, a couple of eigenvalues, which indeed have this form. And here we have to look, in fact, that there is, since the discriminant function delta is positive for mu small enough, so here we have a real part, which is non-zero. And then, so these are the discussion of the two eigenvalues, precisely the shape it has at epsilon fixed. So we have that these eigenvalues starts from here when mu moves, it makes this shape of the 8, it reaches then intersects again the imaginary axis, and then after that it remains on this axis. So then there are two other eigenvalues. The two other eigenvalues close to zero have explicitly this shape here. They are purely imaginary. And then when, in particular, when values of mu moves, okay, also these, so they will span, they will remain always on the imaginary axis, and then they will span, will remain here. Okay, so these are the two, so in blue one, here we have the two unstable eigenvalues, okay, which I've described. So just a couple of remarks. The infinite depth case, it is not a special case of the finite one. In fact, it turns out that all the expansions that we do, are indeed uniform on compact sets. So the infinite depth case is another story. It has to be dealt differently. And I think that what we shall see it precisely later, but what makes it well, natural, this fact is to look at hyperbolic tangent of h mu. Of course, if a priori, so if a priori I take that h it is equal to plus infinity, well, then whatever is mu, in particular, however small is mu, here I will have 1, and that it is the infinite depth case. On the other hand, if h is fixed, well, so the hyperbolic tangent of h mu, when the Floquet exponent mu is small, well, this gives rise to something which is small in mu. And so this, in fact, I think, well, this is precisely what appears in the Dirichlet-Neumann operator and in several pseudo-differential operator, which I think makes rather clear the strong difference between the infinite depth case and the finite depth one. Okay, but then now after this, I would like now to spend more time, in fact, to explain the main ideas of proof and the method that I think it is extremely natural in this problem, and I think it can be applied in many situations. Okay, so the first observation is the fact that is very general, the fact that the eigenvalues of L mu epsilon with non-zero real part may arise only from multiple eigenvalues of L mu 0. What I mean that if L mu 0 has an eigenvalue which is purely imaginary and simple, then under perturbation of epsilon, it will remain again on the imaginary axis. And the reason it is an Hamiltonian symmetry, and it is due to the fact that since the operator is Hamiltonian, so if we have an eigenvalue lambda, then also minus lambda complex conjugated is an eigenvalue. And then we cannot have, so if the eigenvalue on the imaginary axis is simple, under perturbation, it cannot split into others because this would violate the counting of this multiplicity. So the first thing to look at is to look at the spectrum at epsilon is equal to 0, and to look when, so the spectrum of the operator L mu epsilon, that in this case it is this matrix of pseudo-differential operators, whose eigenvalues are explicitly written here, and to look when they may be, when they are not simple. Well, here it turns out that in particularly for mu is equal to 0, there is the eigenvalue mu is equal, there is the eigenvalue 0, which is not simple, and actually it has a multiplicity 4. The multiplicity 4 is a consequence of the fact that the Stokes waves appear, in fact, in 4-dimensional manifolds, and they are, in fact, they give rise to this eigenvalue with algebraic multiplicity 4. It turns out that then there are 3 explicit eigenvectors and 1 generalized eigenvector. So 0 is an eigenvalue, defective, with 3 eigenvectors and 1 eigenvalue, generalized eigenvector. Okay, and so the problem is how we can determine how the eigenvalue 0 splits when epsilon is different from 0 and when mu is different from 0. So the natural tool is perturbation theory of separated eigenvalues, developed in quantum mechanics since since the beginning of quantum mechanics, and then brought by Cato to a very beautiful level of rigor. And okay, so here we shall start from that Cato theory of perturbation of separated eigenvalues that I will describe, and then we shall make the observation, which was not done, which is not done in the book of Cato, that actually for Hamiltonian operators like the one that we encounter, Cato theory has preserves all the symplectic aspects of the reduction. So the Cato reduction preserves the Hamiltonian, the symplectic, and also the reversible structure. And this, so in fact, it shows, first of all, how natural is this construction. And okay, also it will be an enormous advantage because it will imply to study matrices 4 times 4 dimensional, which a lot of structure, which is in fact so the item 2 of this observation. And then the other procedure that I wanted to describe, also this is a very natural idea, I think, well, it is algorithmic method, which is the in one of the essence, probably one of the major ideas of Kolmogorov-Arnold-Moser theorem in another setting, an algorithmic method in order to diagonalize perturbatively matrices. So if I have a perturbation which is diagonal or block diagonal plus a perturbation, which are systematic conditions in order to block diagonalize, because of course that it is an important, an important systematic procedure. Okay, so I will discuss before starting with the proof. In fact, I just mentioned again here the fact that the finite depth case is more difficult, as we shall see, than the infinite depth case. And the reason is the fact that the four eigenvalues of L mu epsilon, L mu 0, when mu is small, so we said that when mu is equal to 0, we have the 0 is the only eigenvalue. Well, so when mu is different from 0 but smaller, these eigenvalues split, but they have all the same size order mu. Whereas in infinite depth, it turns out that there are two eigenvalues which are order mu and the two others which are indeed of order square root of mu. So they are much larger. So there are two eigenvalues which are mu. So here it is the complex plane. There will be two of them which are order mu. And the other ones in infinite depth are much larger, square root of mu, square root of mu. And this separation of the spectrum makes it appears it is important in KM theory because if two eigenspaces corresponding to eigenvalues which are much, if the two eigenspaces correspond to eigenvalues which are much separated, then they can be decoupled under much stronger perturbation. But then this I will explain it later. So the other comment, it is in fact and these consequences in fact has before the fact that in infinite depth square root of hyperbolic tangent of mu is square root of mu, whereas in finite depth mu hyperbolic tangent square root of mu hyperbolic tangents of mu is linear in mu, so it is only order mu. This was the previous observation. Okay, but then I start with, I think, the method, which probably is the most, I think, probably interesting at least now. The method, which is, I repeat, extremely natural, and I hope can be used in several contexts. Okay, so as I said, here we have the operator, the unperturbed operator L00, which has an eigenvalue. In this case, it turns out that it is so 0 is an eigenvalue. Okay, we said of multiplicity 4, whereas but the other part of the spectrum is separated from it. That is why we call perturbation theory for a separated eigenvalue. So I wanted to know how the eigenvalue 0 splits under perturbation here of two parameters, epsilon and mu. In this case, in which the other portion of the spectrum is far away. Okay, then it can be interesting also to look at how it splits, if it splits only switch it on one of these parameters. So if mu is equal to 0 and I move epsilon, well, actually, it turns out that actually, in this case, the eigenvalue 0 does not split, because it turns out that the operator L0 and epsilon has indeed the eigenvalue 0, still the eigenvalue 0. What changes is the algebraic multiplicity, so that there are in fact two real eigenvectors. There are two real eigenvectors and two generalized eigenvectors. This, by the way, corresponds also to well, okay, it corresponds to the structure of the invariance, four-dimensional invariance described before. The fact that it is an Hamiltonian system, and also this has an analog in KM theory, which is the KM normal form. Okay, so also this is a very general, beautiful fact here proved by Inge and Stokes. So it means that when mu is equal to 0 and we only switched on epsilon, the eigenvalue 0 still remains fixed at 0. The other eigenvalues are slightly changed by epsilon, but 0 has not moved. So we would like to understand what happens for mu different from 0. And so, okay, here I will go with calm, because it is precisely approach for making a proper perturbation theory of eigenvalues, and it is that I wanted to describe precisely. So what we shall do in order, so we have the zero eigenvalue, then we have the other eigenvalues here. So how to understand the splitting of the splitting of the eigenvalues close to zero, of the four eigenvalues close to zero, not 6, only 4. How do they split? 1, 2, 3, 4. So the recipe, the construction of Cato is the following. One defines the p mu epsilon, which are these operators here, which are the integral of the resolvent on a curve gamma, which separates the spectrum that the eigenvalue that we want to analyze from the other. We remark, okay, so this is the resolvent. Lambda, of course, so we're integrating in lambda where there are no eigenvalues, so all the path gamma belongs to the result, to the outside of the spectrum, to the resolvent set, and so it is well defined, this operator here. P mu epsilon turns out that they are indeed the projectors. So P mu epsilon squared is equal to P mu epsilon. And, well, of course, they commute with L mu epsilon. Of course, because P mu epsilon is a function of L epsilon, and then they commute. Moreover, these operators here are analytic in mu and epsilon once the operator L is analytic in epsilon and mu. The operator L is analytic in epsilon and mu as a consequence of the fact that the Stokes waves is analytic in epsilon, the fact that how it enters in mu. And then here, the inverse operator, the inverse is an analytic function. So, and then I'm making the integral. So P mu and epsilon are analytic, are projectors, which are analytic in mu and epsilon and commute with L epsilon. And then we have the phase space. So how to study then? So then one takes the phase space H1, which is the domain of our operator. It splits into the direct sum of two subspaces, which are the range and the kernel of this projector. And since the operator P is commutes with L, it turns out that they are both invariant. So the phase space, so here there is the range of P mu epsilon that I've called nu epsilon, and then there is here the kernel of P mu epsilon. Both are invariant. So L mu epsilon acts invariantly here and here. So it's clear that and it turns out that the spectrum, so the spectrum of the operator L mu epsilon will be the union of the spectrum of the operator L mu epsilon on the subspace nu mu epsilon, union the spectrum of L mu restricted on the other invariant subspace, which is the kernel. And it turns out that in fact the portion, so the spectrum of L mu epsilon restricted to the range of P mu epsilon is the portion of the spectrum inside the circuit gamma, whereas the other one is the portion of the spectrum outside. So it means that here, when mu and epsilon will move, there will be okay 1, 2, 3, 4 eigenvalues which moves, but these will be the eigenvalues of the operator L mu epsilon restricted on the range of the projector P mu epsilon, and here everything remains completely analytic. Okay, so how can one study the range, how can one study these four varieties, these four eigenvalues? So the projectors P, mu, epsilon varies analytically with respect to mu and epsilon. So P, mu, epsilon is similar to P00 because, okay, they are close, and two projectors which are close are similar one each other. But then there is an explicit similarity transformation, which is this one, which is been produced by Cato, which tells that, in fact, it is an explicit isomorphism, is an explicit transformation of similarity, which conjugates the unperturbed projector P00, on which we know everything, with the perturbed projector P mu epsilon. And by the way, this is the projector on the, we said before, but it is repeated, so that it is the projector on the eigenspace, on the generalized eigenspaces corresponding to the eigenvalues inside the circuit gamma, so which are close to zero. So the projector P mu epsilon, it is in fact similar to P00 through this explicit similarity transformation. And the nice fact of these similarity transformations is the fact, well, it is explicitly, and also this is analytic in epsilon and mu, because P mu epsilon, this is analytic, then the definition of this operator has with the power -1/2, it is a power series, so also this is analytic, and here the same. So in particular, we have, okay, then, so what is above, it tells us that, so we have here P00, then here we have U mu epsilon, here we have, let me see if I've written in the correct order the thing, so it tells that if I take U and then I apply P, yes, it is the same as applying first P. So we have this commutative diagram. And then, okay, and then these are isomorphisms. So the, okay, and then they maps the kernel of P mu epsilon into the kernel of P mu epsilon, the ranges of P mu epsilon, the ranges of P mu epsilon. In particularly, we are interested in here in the range, and so in particularly the range P mu epsilon, it is in fact the image through the isomorphism U of the range of the unperturbed range nu 0, 0. But the nu 0, 0, we know it explicitly because the unperturbed operator was explicit. It had four, for example, we had written before explicitly four explicit eigenvectors, three eigenvectors and one generalized eigenvectors, which are these F1 plus, F1 minus, F0 plus, F0 minus, and then they are transformed by similarity through U. So this is an explicit basis of the nu mu epsilon, of the range of P mu epsilon, which is analytic in epsilon and mu. So analyticity is not lost by this transformation. What is dangerous for analyticity? Well, also, it is, of course, if one would like to follow the single eigenvalue, because the single eigenvalues, when they collide, well, at that point, it can appear any bad things. But in fact, the proper receipt of Cato perturbation theory is that one should not follow the eigenvalues, but one should follow the generalized eigenspaces, and then and this reduction is completely analytic in epsilon. And then I mentioned it before, so Cato in his book make this for essentially in the self-adjoint case, the one of interest in quantum mechanics. What turns out of this construction for an Hamiltonian operator? Well, it turns out that if we have an Hamiltonian operator, which is, as I said, remind J times self-adjoint operator, well, it turns out that the previous projector are indeed skew Hamiltonian. They satisfy this property. The reversibility structure is also preserved, and the similarity transformation of Cato by explicitly one can check that they are indeed symplectic. symplectic satisfies this property here, and also they preserve the reversibility. So so the Kato reduction preserves this beautiful algebraic structure. And then what does it imply? So for example, it implies the following, that the transformations, that the basis that I have defined here, which is analytic in epsilon, has also a property that we call to be a symplectic and reversible basis. What do we mean? So the unperturbed basis is symplectic if they satisfy these properties here, which are the usual definition for the Darboux coordinates in Hamiltonian systems. These and these others, and it is easy to reversibility is this one, and then it is easy to check that since the similarity transformation u mu epsilon are symplectic and reversibility preserving, they preserve along for any epsilon and mu, they preserve these two properties. It means that for any epsilon and mu, this basis is still symplectic and reversible. And this has another important consequence, that so we said that we wanted to look at the restriction of this operator on the four-dimensional subspace nu mu epsilon. Well, but an operator is represented, it is simple to check that it is represented in a symplectic and reversible basis by a matrix, a 4x4 matrix, which has an extremely simple structure that we call again Hamiltonian, because their normal form is the following. We have J4, which is this explicit Hamiltonian matrix. J2 are these 2 times 2 here symplectic matrices, and the B mu epsilon is a self-adjoint matrix. So at this point, we are reduced to determine the spectrum of a 4x4 Hamiltonian matrix. And since it is also reversible, this is also another nice algebraic structure, that this is real, this is purely imaginary, this is real, this is purely imaginary, and so on. And they alternate. Okay, so this is a good point, but still a spectrum of a 4x4 matrix can still be rather complicated, even though it has structure. And so how do we proceed? So our procedure that so far I would like to describe it is a completely algorithmic. So this would enable to compute rigorously everything. There are no approximations at all. Is the following. So, okay, in fact, there is now the time is going too short, but I would like to reach. So then at this point, it is important to look at what is the structure of this 4x4 matrix. Then this is a computation which is which has some. It is not just a Taylor expansion. It is a delicate expansion, but then one can prove that it has the following form. So it is these are 2 times 2 matrices which have this form here. Okay, so of course, what one has to look from here. So one look at, so we have a 4x4 matrix, and so here is the idea of say KM theory. We would like to see if well. So let us start first looking at the spectrum of the 2 times 2 block diagonal parts. So, for example, the spectrum of the 2 times 2 block in the top left turns out to be this one. You see that here the diagonal terms are exactly the same. This is a consequence of the fact that we have preserved the Hamiltonian reversible structure. So they determine the spectrum, just a translation. So the spectrum of this is extremely simple because it is just the spectrum. It is only determined by these 2 off-diagonal terms. And in fact, it is the square root of the product between the 2 off-diagonal terms. And then in particular, they have eigenvalues with non-zero real part if and only if the signs of these and the signs of these 2 terms are the same. Because the eigenvalues of a matrix, which is, so here, 0, 0, alpha, beta, of course, the eigenvalues are square root of lambda, alpha, beta. Okay, and then, Okay, and then we want if alpha and beta have the same sign, then there appears eigenvalues with the non-zero real part. So to see if this is possible, okay, here you mentioned here e2 is positive, so this term here is always negative. And so here, well, there are some hope because, yes, there are some hope because also E11 is always positive. And so if mu is small enough, okay, so this is negligible. So if mu is small enough, they have the same sign because they are both negative. However, okay, that is, so the 2 times 2 top matrix on the top has these 2 eigenvalues. It turns out that the 2 times 2 matrix in the top below has purely imaginary eigenvalues. Okay, but then we have to, of course, determine the eigenvalues of the 4 times 4. And so the idea is to make a block diagonalization algorithm, that it is KM theory idea. Even though, okay, in the finite depth case, which is more difficult, there will be a non-perturbative correction in this block diagonalization argument. In fact, these ones are not already the correct Benjamin-Feir eigenvalues. So, okay, probably now I skip, by lack of time, the way in which we make this expansion. I only remark that it is not just a Taylor expansion. And okay, there are some delicate points in order to show that there are at any orders, there are never some points. And then in these few minutes, I discuss, in fact, the block diagonalization algorithm, and to make a block diagonalization of this 4 times 4 matrix, trying to kill the off-diagonal terms. In this process, in finite depth, there will appear in the off-diagonal, will appear corrections on the diagonal which are significant. So now I would like to implement an algorithm which will conjugate this into a matrix which is a block diagonal in a perturbative with for some other G tilde and J2 G tilde. Of course, if we do that, we are in business. And this transformation that we wanted to do, we wanted to make it symplectic because we wanted to preserve the Hamiltonian structure. We wanted to make it still reversibility preserving because we wanted to preserve the reversible structure. Because, like here, a 2 times 2 reversible Hamiltonian structure has a spectrum which is explicit. Extremely simple. Okay, and then let me go to the idea in these few minutes. Okay, after a symplectic rescaling that, okay, which is this one, but here I skip. Okay, so this is the other ingredient. So we split the matrix. The Hamiltonian matrix is D1, which contains the diagonal part. And then to this we add the R1, which is the perturbation, because are the off-diagonal terms. So we would like to make an algorithm which kills the off-diagonal terms, diagonalizing. Then, since nu epsilon is Hamiltonian, it is natural to conjugate through transformations, linear transformations which are symplectic, so that it conjugates Hamiltonian matrices into Hamiltonian matrices. Symplectic matrices are in R4 the flows of other Hamiltonian matrices, so the exponentials of Hamiltonian matrices S1, and then S1 is our unknown. So we look for S1, which will generate this with its flow, this symplectic matrix, in order that the new Hamiltonian reversible matrix has a simple structure. In particular, we would like to eliminate these off-diagonal terms, or at least in a first step to make them smaller. So an Hamiltonian matrix has this form, and then we implement the expansion of this matrix. So this is a conjugation. So the way in order to look at it is to make well, the Lie expansion approach. So how it is done? L2 mu epsilon is the following. It has the following Lie expansion. First, the unperturbed term, D1. Then appears the commutator. So then there is this one, which is on the diagonal, and then the unperturbed of diagonal term, which is this one. Then appears the commutator between the generating S1, the auxiliary vector field, which generates our symplectic transformation, and the unperturbed diagonal operators here. Then there are other terms. I remind one thing: we choose by the Hamiltonian matrix, which generates the symplectic transformation that we look for, of the same off-diagonal form of the terms that we want to eliminate. Doing that, it turns out that the commutator between our unknown S1 and the diagonal part, in fact, this commutator turns out to be only off-diagonal, and then it will be able to kill the off-diagonal terms, which is original in the equation. We make the expansion of that second line given above. We obtain these 2 times 2 matrix, which are these ones. And then now we aim to look at a matrix, sigma, in order to solve this equation that we call homological equation, say. Okay, and then looking for sigma again in the Hamiltonian form J2x, this leads to look for a 2 times 2 matrix x, which solves this equation, linear equation, which is in algebra is called the Sylvester equation. Okay, in order to solve the Sylvester equation, there are necessary and sufficient conditions to solve it. It is important, it is necessary and sufficient that the spectrum of d0 and d1 are separated. Okay, here we solve it explicitly, and then now I skip that, but then we obtain this, we solve it explicitly. So this produces the first order S1 vector field, which has killed, at least at the first iteration, has killed this completely the off-diagonal term. Now we have chosen S1 so that these terms completely zero, which is the main off-diagonal contribution. In finite depth, this will produce another correction on the diagonal, which is not negligible, and which actually it is the one which gives the exact account of the correct number of the Benjamin-Feir instability. Then appears other off-diagonal terms, but which are, however, are of much smaller size. Then an implicit function theorem construction, either construction, either iteratively or just by an implicit function theorem, will after that, completely after that we have eliminated the first contribution, will iterating this procedure that is applied the implicit function theorem, will enable to completely diagonalize the system into a 2 times 2 block diagonal into 2 times 2 blocks, where both U and S are 2 times 2 matrices, which are both Hamiltonian and reversible. So this, at this point, we have a completely, in an algorithmic way, analytical way, completely diagonalized the system. The spectrum of this is equal by similarity to the spectrum of our original problem. We have lost nothing, and then everything that, okay, and then we can go back. We are in the best possible coordinates now, where the system is diagonalized, and we have a completely explicit transformations on how this is conjugated to our original system. So this provides all the possible information we wish on the spectrum, on the eigenfunctions, or generalized eigenfunction, and so on. And then this is the end. U, because it provides the eigenvalues of U are the unstable ones, S, the 2 eigenvalues are the stable ones. And thanks a lot for the attention. I hope to be still in time.
Okay, so maybe we'll have some time for questions.
Sure.